Hello everyone, and thank you very much for joining this presentation. My name is Sara Garcia Sanchez, and I am a PhD candidate at Northeastern University in Boston under the guidance of Professor Kaushik Chatri. So in this presentation, I'm going to present my recent work called Camera-Enabled Joint Robotic Communication Paradigm for UAVs mounted with mmWave radios. So first, this is the outline that I'm going to be following throughout this presentation. I'm going to be talking about first the scope of this work, followed by an overview of the proposed approach. And after that, I'm going to give the details of the joint robotic communication framework that we are proposing here. And I'm going to finish with the performance evaluation. So in recent years, we might have noticed that there has been a huge increase in the number of Internet of Things deployments, as well as the number of wireless devices that we use in our normal life. So for that reason, the bandwidth available at the sub-6 GHz band is not longer enough to satisfy the capacity requirements that we have now. For that reason, people have been looking at higher frequency bands where there is a large amount of available bandwidth, such as millimeter wave frequencies. However, we know that at millimeter wave band, signals suffer from different conditions, such as increased free space path loss and also a drastic power loss caused by the presence of obstacles between the transmitter and the receiver. This is forcing to deploy or have very costly and lengthy deployment plans to be able to maximize the probability to have line of sight conditions in millimeter wave deployments. So one of the solutions that has been proposed is to use UAVs. So essentially, this solution consists of mounting the transmitter, receiver, or both on a UAV. And then whenever an undesirable condition happens, such as an obstacle between transmitter and receiver, the radio can be moved, taking advantage of the flexibility of the UAV platform. So here I'm going to be talking about why this UAV-based system might be challenging. The reason is because at millimeter wave frequencies, signals suffer from high free space path loss, as well as large atmospheric attenuation. In particular, in the 60 GHz band, which is the millimeter wave unlicensed band, there is a peak of atmospheric attenuation. And these two factors combined with the small antenna apertures at high frequency limit the amount of received power that we have in a millimeter wave band. And so to overcome these additional loss that we have at higher frequencies, one of the techniques that is used is to pack the radiating elements in what we call as antenna phase arrays. And with such antenna phase arrays, we are able to use a technique called as beamforming, which is capable of directing or suppressing the energy towards the receiver by shifting the phase on each of these radiating antenna elements. So essentially, using that, we are moving from having omnidirectional transmissions to directional transmissions. But because of that, we need beam alignment between transmitter and receiver. So the standard beamforming procedure for this beam alignment process is called sector level sweep, and we also refer it to as beam sweeping. So in this process, transmitter and receiver are going to sweep all beams within a code book. So each of the beams point to a different angular direction. For each of the beam pairs, the transmitter and receiver measure the received power, and eventually when they finish the whole angular sweeping, the pair with highest power is going to be selected for establishing communication. Now, the challenge here comes when we use UAV for establishing the link. So even when a UAV is commanded to stay at specific coordinates, GPS error causes a constant UAV motion. which can be up to several meters. And this is related to GPS errors that are affecting the navigation system of the UAV. So whenever the UAV moves, this is going to cause beam misalignment and is going to often trigger the SLS procedure. And during this SLS procedure, the communication link is disrupted. So this is going to drastically drop the overall throughput of the communication link. So in different research areas, people are looking at different solutions. In the RF domain, the typical solution is to estimate the angle of arrival and then point the beams toward that angular direction. But this solution typically offers limited angular resolution. In the robotic domain, solutions are trying to enhance the UAV stability. Now, the issue here is that there is not going to be an immediate reaction from the wireless communication system. So in a case such as a wind burst, there is no a quick fix or a quick reaction in the wireless domain. And finally, we have the multimodal domain, which combines different types of data, such as visual with RF or sensor inputs. But one of the limitations is that so far they do not exploit the high resolution of mmWave beams. So now I'm going to be talking about an overview of the proposed approach. So in this way, we try to answer the following research question. What if the beam pattern shape could guide us towards the rotation and UAV needs to perform to maintain beams aligned at all times? So this idea is trying to exploit the trade-off that exists between the directionality through narrow beams and the resulting irregularity on the beam pattern side lobes. So in order to prove that idea, we measure in an RF anechoic chamber the beam patterns for the teragraph mmWave radius operating at 60 GHz for beam width of 2.8 and 8.5. And we observe that for the narrow beam of 2.8, the beam pattern shows a very irregular shape. So our idea was to try to exploit that information, which is in the angular domain, to be able to rotate the UAV towards the angular direction to keep beams aligned at all times. So this solution comes with three different challenges. The first one is because we need the knowledge of the radiation patterns, but we need a cost-effective beam pattern characterization because characterizing the beam patterns in an RF anechoic chamber is very expensive, but also and very costly. But also the UAV airframe is going to modify the beam pattern, so we need to consider that. The second challenge is the ambiguity resolution between beam misalignment and power degradation. So this is shown with the stars in the diagram that you can see here. So that stars are pointing to angular directions on the beam pattern that has the same level of power, the same gain, antenna gain. And so there is ambiguity, and the UAV could be rotated in completely two divergent directions. The third one is because we are combining the knowledge of mmWave beam patterns with actual rotation on the robotic UAV front. We need the creation of a mmWave robotic framework. And so our proposed approach involved two steps. In the first steps, we are going to use fine-grained data, exploiting this information contained in the angular domain of mmWave radiation patterns. And in the second one, we are going to use coarse-grained data provided by onboard cameras to help solve the ambiguity and rotate the UAVs in the desired direction. So these are some more details on the cost-effective beam pattern characterization. We decided to do the characterization in an on-light state. So be able to characterize the beam pattern during the standard SLS process, taking measurements during flight. And we did that in experiments. So we compare here the beam pattern in an RF chamber at 2.8 degrees with the same beam pattern calculated during the SLS process for also 2.8 degrees. So specifically, the diagram at the bottom is showing the received power for all transmitter and receiver beam pairs. And the point P stars represent the point of minimum path loss or maximum received power. And the row containing P stars contains an approximation of the antenna beam pattern that we are going to use for this work. However, this information was not enough to be able to solve the ambiguity. For that reason, we decided to use visual data collected from a camera at the receiver UAV. And so from that camera, our goal was to locate the UAV transmitter position within the image and use that as a coarse-grained estimation of the relative location between transmitter and receiver. So using that information, we wish to solve the left versus right ambiguity of mmWave narrow beams to make sure that we are not misrotating the UAVs in the wrong direction. Once we take one of the images, we binarize the image pixels, convert it to a grayscale, and then we perform object contouring, noise removal, and bounding box generation based on the UAV aspect ratio. With this approach, we got low performance. Actually, we got misdetection whenever we have complex backgrounds, so no clear scale at the background of the UAVs. And we tried that in real images collected during actual UAV flights using the DJI Zenmuse X3 camera, and we got 29.5% detection accuracy. So in order to enhance that, we use channel and spatial reliability tracking, CSRT, which was taking video for the UAV and performing a tracking over time of the UAV image. And with this combined approach, we achieve a 100% detection on the same real images with complex backgrounds. Next, we also have to solve the third challenge, which was the creation of a mmWave robotic framework. And in this framework, we propose a 3-stage decision framework. So in the initial stage, we would collect the online beam characterization during the SLS process, as I described before. Then in the detection stage, we would monitor the received power and detect power drops to detect beam misalignment. And finally, in the recovery stage, we would estimate the correction based on camera video and the beam characterization that we did during the SLS process, and then command both UAV to start synchronized motion through the robot operating system ROS. So we decided to use this robot operating system ROS because it provides a high-level communication between UAVs, but also low-level communication between sensors within the same UAV. And we use two different functional blocks in here. First, the algorithm blocks, which was responsible of taking the mmWave and camera data, collected it, and returned the required rotation that both UAVs need to perform. And finally, the ROS block, which was responsible of the communication between UAVs. So this would first command the UAV motors at the receiver side, and then publish the commands to a ROS topic to which the transmitter was subscribed to share this required rotation with the transmitter. And so they could start synchronized rotation and align the beams. Finally, I'm going to be presenting the performance evaluation. So in our emulation setup, we generate a UAV to UAV link within the ROS environment. The UAVs relate on noisy GPS data for navigation, so to make sure that they suffer from translational displacement, and there was hovering, and so that hovering was created the beam misalignment. And then we also equip the UAVs in the simulator environment with noise-free GPS data, just for the true locations for our baseline. And eventually, we collected the video at the receiver UAV using the GasVivo simulator. So here are the results that we got from our simulator. We actually compared 3 different approaches. The first approach was the standard beam sweeping, so the SLS process. So that means that whenever the power dropped below a threshold, the SLS process was triggered, and so communication was disrupted. The second approach was our proposed approach, in which we detect the power drop and then we initialize the required rotation between the UAV transmitter and the receiver after calculating the required angle to be rotated. And so one of them considered the perfect radiation pattern knowledge, and the second one is considering that we don't know the actual perfect radiation pattern, but instead we are using the heat map radiation pattern, which is the beam pattern characterized online during flight. And so we observed that the standard beam sweeping causes a very high average latency and low physical bitrate throughput compared to our proposed approach. And certainly, if we know the perfect radiation pattern, we are going to get better performance compared to the approximation. In the figure in the middle, there is the link logs over time whenever we take no action and with the three different proposed approaches. So the power drops that you see here are whenever the beams are aligned, and then the link loss drops are close to zero. And so from this result, based on our emulation, they demonstrate the beam alignment with typical errors lower than 1 degree and 33% improvement on the link physical bitrate compared to the standard approach. So as conclusions here, we have presented a multimodal framework which leverages mmWave, visual and sensor data to track mmWave narrow beams in UAV to UAV links under typical mobility conditions. And we propose a framework to achieve seamless fusion of multimodal RF hardware and sensors combined with the ROS framework. We propose a two-step method to perform high-resolution real-time beam tracking, combining coarse grain data provided by onboard cameras and fine-grained data, exploiting the information contained in the angular domain of antenna radiation patterns. And we design a fine-grained method for detecting relative displacement by building in situ radiation patterns of the mounted antennas. And finally, our results based on raw simulation demonstrate beam alignment with typical errors lower than 1 degree and 33% improvement on the physical bitrate compared to the standard approach. So this is all from my side. Thank you very much for your attention. Please feel free to ask any question. I will be happy to try to answer. Thank you.